Okay, let's get started again. So we kind of did this last class, this f of s right here. And if you remember, right, we know that it's going to have something, right, if we factor it all the way down. The problem is you can't just say that it's a and b, because anytime you have a higher order coefficient than 1, so you can see that it's s squared, you can't just say that it's a over s squared plus 4 times b over s plus 4, because the partial fraction expansion, when you combine them together, they won't actually end up working. So what we did in this case here was we actually did partial fraction expansion all the way down to the base roots, which works perfectly fine. You can do s plus 2j, s minus 2j, and s plus 4 and do partial fraction expansion doing the normal technique. That's perfectly fine to do, all right? So you can certainly do this. The problem becomes when you get to here, right? If I want to take this back into the time domain, I'm going to have something that looks like this, 1.12 at an angle of 26.57 e to the minus 2j, right? Kind of loud. I hope that's not picking up on the, is it upstairs or downstairs? What's that?
Oh, I think they're working. Well, they were working in the PLC lab yesterday, so I'm assuming it's right.
Oh, okay. Well, if it continues, we'll have to ask them to delay at a later date and time. So if it's e to the minus 2j, right, is that a real world system or signal? No, it isn't, right? There's no such thing as e to the minus 2j, is there? So what we did here is we combined those two to get an s squared plus 4. And if you look at the Laplace table, there is something that has an s squared plus omega in the denominator. And that equates to a sine function, right? As long as you have omega here. And sine waves and cosine waves exist, right? Those are things that we can build. We can go put them, make a function generator downstairs, put an oscilloscope on it, and we can easily get a sine wave or a cosine wave. It's just that this 2j is where it doesn't work. So this is one method to go ahead and solve for if you have essentially complex roots, right? Because when we did the quadratic equation, we had s squared plus 4. If we do the quadratic equation, we have plus or minus 2j, which means we have complex roots. So if we have complex roots, this is method number 1. Our next method is method number 2, which works and was probably, if you've taken differential equations, how you would actually solve for this as plus b, okay? This is a valid partial fraction expansion. So how do we do this one? Well, we're going to go ahead and solve for b first. So we're going to multiply both sides by whatever is under the as plus b term. So we're going to multiply it by, s squared plus 4. And we're going to evaluate that not at s equals minus 4, right? What we're going to do is we're going to evaluate that at 0 here. And the reason why we do that is because this term goes away, right? A times 0 equals something. And you can say, hey, wait a minute, Paul. What about our c term? Well, from our previous work, the c term that we solve for is right here, -2. So once we've done partial fraction expansion, regardless of if it's as plus b or a over s plus 2j over b plus s minus 2j, the c term doesn't change, right? Because it's s over 4. So this c term that we stole, we calculated the -2, we actually are going to substitute that into here. Okay? So we can immediately solve for as and b because we have solved for c. So the first case we solve for is b equal to 2 because we want to get rid of the a term, right? So multiply both sides by whatever is over the s squared plus 4 and evaluate it at s s equals 0. So you're going to multiply that 0 term, and all you're left with is b at that point. To solve for a, once I have as over s plus 4, this is b now, right? We have 2 minus 2 over s plus 4. How would you solve for as plus 2? I mean a at this point. Well, if I multiply both sides by s squared plus 4, right? Those terms will cancel, so I'm left with as plus 2 minus 2 times s squared plus 4 over s plus 4 equals 10s over s squared plus 4, right? All I have now are two variables. I have a and I have s. This is a linear system. Yes, sir?
Wouldn't the 10s just be over s plus 4 not?
S plus 4, yep, thank you. Not s squared, but s plus 4. Let me cheat this over a little bit so I can see. So this is a linear system, which means any value I plug in for s and solve for a value of a, it's going to work. That value of a is valid throughout. So I can pick any value of s I want and solve for a, and it works for me. So why not evaluate it at s equals 1? Right? 1's an easy enough number to work with. So I have a times 1 plus 2, minus 2 times 1 squared, which is 1 plus 4 over 1 plus 4. It's going to be equal to 10 times 1, which is 10 over 1 plus 4. So a equals 2. I'm off my game, I guess, this morning. So a plus 2. Now I've got to figure out what's in here. So I got a 1 plus 4 and a 1 plus 4. Those just divide out, don't they? Just because they're numbers, it doesn't mean they didn't divide out. They're still multiply. So that's a nice thing about picking 1, right? Because it's 1 plus 4 divided by 1 plus 4. I can just make that equal to 1. So this becomes minus 2 equals 10 over 5. So a equals 2. Okay? And that one works out perfectly well. So if you were going to go to do partial fraction expansion, right? We want to go to the inverse Laplace. The first thing we need to do is s squared plus 2 squared plus 2 over s squared plus 2 squared minus 2 over s plus 4, right? Because in your Laplace table, we have omega over s squared plus omega squared is the sine of omega t, and s over s squared plus omega squared is cosine of omega t. We don't have one that has an s plus 2 in there, right? Not without having a real part in its root. So we had to break that 2s plus 2 into two separate terms. So we have a sine and a cosine. So now what we see is this looks pretty darn close to this one, except it's being multiplied by 2. So the last thing I'll do is I'll move the 2 out front. Now, can I get a little help as to bring this back to the time domain? Because this looks really close to the table. 2 cosine 2t plus 2 sine 2t. Are you sure? This is sine of omega t. Omega, we say, is 2. Right. Don't I need a 2 up here? to make it be omega over s squared plus omega squared?
Isn't that second term 2 over s squared plus 2 squared?
It's 2 over s squared plus 2 squared, right?
Oh, so it'd be the
But over here, I have no idea why it keeps doing that. This is omega. So if we go s squared plus 2 squared, right? That tells me that omega is equal to 2. I had darn well better have a 2 up there, right? So this is going to be equal to the same thing as 1 times 2, which is just the sine of 2t, isn't it? It's not being multiplied by 2. It's just being multiplied by 1.
wasn't that what I said?
I think you said 2. You started to say 2 sine.
Oh, I meant sine.
Okay. Sorry.
No, that's my bad.
Okay, then the next one. Do you see an s squared in there? So what does that look like in the table? S, 1 over s plus alpha is e to the minus alpha t. So what is this? Minus 2 e to the minus 4t is your f of t. Okay? Questions on that? I have a question if you don't. Does that look like this? Sure does. Right? Looks perfectly like it's supposed to look. So, yes, we got the right answer. Okay? There's one last way that we can do it. And this is the way that we recommend you do it in this class because it simplifies the work. What if we said, okay, we're going to do partial fraction expansion again. So let me write that out. I'm going to do 10s over s squared plus 4 times s plus 4. And this is going to be equal to, so now I'm going to start differently. I'm going to just say this is c over s plus 4. That value doesn't change from the previous work. But now I'm going to actually call this not bs plus c. I'm going to call it b at an angle of theta. Why do I do that? Do you remember back in trig, this was the cosine axis and this was the sine axis? If I had a cosine part here and a sine part here, how did I get this corresponding vector? Let's just say that this is x cosine and y sine. How would you convert that to a value? That's one way. You could do x squared plus y squared, but that only gives you the magnitude. It's a vector, right? How about just do x plus jy, right? So if I have an x plus a jy, that's going to be equal to now, let's go with Kyle was saying, some magnitude at an angle of theta, right? That goes from here. This is theta. What if I went from here? It's 90 minus theta, right? It's a little bit different. So let's go back again. So keep this in the back of your mind. Keep this part. This is important for us. Keep that in the back of your mind because do you remember omega over s squared plus omega squared? What does that look like in the tables? What is that in the time domain? Sine of omega t, right? And my output waveform I had here, whoops. It's going to cause me some agita here. There we go. My output waveform over here had a sine wave and a cosine wave, right? 2 cosine 2t plus sine of 2t. If I can recognize that sine of omega t and the cosine of omega t that I had, if I can combine them and reference the sine axis here, then essentially all I need to do is that b at an angle of theta term that I have, it's going to be the combination of the x plus jy. So our original one, we had 2 cosine. Let me sit down and write this because I can make it a little clearer. So I have 2 cosine of 2t plus sine of 2t, right? This element here is multiplied by 1. This element is multiplied by 2. So if I was going to combine these into a vector, I would go 2 in the cosine direction and 1 in the sine direction, right? That will give me a corresponding magnitude, as Kyle was talking about earlier. Normally, we do our angle here. This would be the angle that we're talking about. But as we mentioned, this here, this is omega over sine s squared plus omega squared. That is a sine term, which if I'm keeping track of my axes, this is the sine axis. So I'm actually looking for the angle theta here. So I combine these two to be equal to sum b at an angle of theta sine of omega t. And why do I do that? Because when I have a term that has complex roots, whoops, just 2, that I have to do partial fraction expansion, I do not want to do as plus b. I do not want to do s plus 2j, s minus 2j. This was approach 1. This is approach 2. What I'm going to do is approach 3, which is this is going to be s squared plus 2 squared, and this is going to be some complex number. How do I solve for the complex number when I do partial fraction expansion? My b at an angle of theta is going to be equal to my original function, which is my f of s. I'm going to multiply that by my s squared plus my omega squared. In this case, it's 2, right? So whatever the complex root is. And then I'm going to evaluate it at s equals a positive j omega. All right? When I do that, b is going to be b at an angle of theta is a complex number. So method 3 is the most efficient because it combines the sine and cosine into one step. I don't have to do all that stuff over again. So let me see if I can zoom out. Why won't you zoom out? And then zoom in over here. And remember what I said? I took and combined the magnitudes, right? The 1 squared plus 2 squared because there's a cosine of 2 and there's a sine of 1. And then I take my angle here, which is my angle, which is the inverse tangent, and I get this value here, that 26.57. It's referenced to the cosine axis, right? So this is 2, 1. This angle here is theta, which is 26.57. If I want this one, I just have to go 90 minus theta. So my angle becomes, when I combine those two, right, is just going to be 2 plus 2, 4, sine of 2t plus my 63.43 degrees. That will be the exact same approach if you went and did b at an angle of theta is going to be equal to my f of s, which is 10s over s squared plus 4 times s plus 4, evaluated at s equals j2. Right? Does that make sense what I just did? This is my original f of x way up here that I'm trying to do partial fraction expansion. I'm trying to solve for b at an angle of theta. So I take my original f of s, which is here. This is my original f of s. I multiply it, right, by s squared plus 4. So I need to multiply it by s squared plus 4 because that's going to be whatever's under the complex term. So that will cancel. That will cancel. And then I evaluate at the positive root here. The positive root. Since this is 2 squared, right, we know we have plus or minus 2j. So I'm going to use the positive root. So my b at an angle of theta is equal to 10 times j2 all over 4 plus j2. Anybody has a handy dandy calculator out? Can help me out? Stop it. So it's going to be equal to, let's write that again, 20j over 4 plus 2j. What do you get? And please put that in radian, and make sure your calculator is in degree mode and displaying in polar form.
I'm getting 4.85 at an angle of 75.96.
4.85.
I have 4.47 and I think it's 63.4. Yeah, I got that too.
Oh, I did one eye on the bottom.
Thank you. Okay. So 4.47 at an angle of 63.43. Oh, that's good. The angle checks out in our result, right? That's a good thing. Uh-oh, did I make a mistake? You told me the answer was 2.24, not 4.47. Did I screw up? Did I screw up? Well, let's go back to our f of s, and we're going to write it in expanded form. We have 4.47 at an angle of 63.43. This is going to be multiplied by 1 over s squared plus 2 squared minus 2 over s plus 4, right? That's our original function. So that's what we have for b and at an angle of theta and c. Did I make a mistake? Anybody? I should have 2.24, but I have 4.47. Where's my mistake? What was the sign of omega t in the Laplace domain equivalent to?
Omega over s squared plus omega squared.
Very good. It's omega over s squared plus omega squared. Is this omega? Omega is 2. Don't I need a 2 up here? I just multiplied that by 2. To make sure that I don't change anything, what else do I have to do? I have to divide that by 2, right? Buy that for $1. So now this is all set up in standard form. So now I can solve for my f of t, which is 2.24, the magnitude, sine of 2t plus 63.43 degrees minus 2e to the minus 4t. This is method 3. Works very efficiently. You don't have to do the same level of partial fraction expansion. Easy peasy, lemon squeezy.
So don't worry about 1 or 2, just use 3.
Just use method 3. It's much faster. And does this exist in the time domain? Anybody? Yeah. Absolutely. It's just a phase shifted sine wave. So what, right? We do phase shifting in sine waves all the time. That just means it starts 63.43 degrees later, right? So, yeah, it works perfectly fine. This is a real world thing. That's why it's easier. So what we're going to do when we do these partial fraction expansion is we're just trying to come up with a very consistent, similar technique, right? We always evaluate f of s. We brought partial fraction expanded so we do quadratic equation. We get it down as low as we can. Then what we do is we actually solve for the coefficients in the numerator by multiplying both sides by whatever is under that numerator, and then evaluating at the root of that numerator, and then we just go. When you do the as plus b, that's a modification, isn't it? Now you have to start saying, okay, well, I'm not just multiplying. I've got to get clever and figure out, do I multiply by 2? Do I multiply by 1? What do I evaluate at? It just gets crazy. This one, you just say, I do the same thing every time. Questions? Any questions?
Can you explain what, again, you're not using the angle from the x-axis, you're using the angle from the y-axis?
Absolutely. Great question. So the question is, when we normally draw vectors, right, we always pick this as our reference vector, right? So this is our theta angle. Always, always, always. But if you recall, when I look at my table, I have omega over s squared plus omega squared is equal to the sine, and s over s squared plus omega squared is equal to the cosine. When I do partial fraction expansion, I'm going to have s squared plus omega squared here, and I'm just going to have a coefficient. I do not want this s in here. This is bad. So if I have an s in here, then I could get the cosine. If there's no s here, I can use the sine. So remember, this is normally our reference axis, but when we do trig, the real axis is the cosine axis, and the imaginary axis is the sine axis. So the reason why I reference it from the sine axis is because I don't want to worry about having that s in the numerator. I want to throw it away. Okay? Want another example of this? Okay, let's just dream one up. So f of s is going to be equal to, let me see. I've got to make it so that it's not too crazy. So let's say it's 5 over s plus 2. Just give me a minute now. Let's see. I want to add that. Hold on, I'm going to turn off screen mirroring so people in TV land will be able to see this, but I just want to make sure that I can do that here. So let me pause the video too as well. So I'll be right back. Be back. So I would like to take this back to the time domain. I want to know, what is f of t equal to? Okay? Right? So the first thing we have to do is, do we have to do partial fraction expansion down here? Yeah, because we have two functions here. We have this function and this function, which are two different f of s's, right? Could actually be 3 f of s if this has two real roots, right? But I have at least 2 f of s's that are being multiplied together, so I can't take those back to the time domain. I have to do partial fraction expansion. So the first thing I'm going to do is my quadratic equation. Negative b plus or minus the square root of b squared minus 4ac. Let's see, that's 52. All over 2a. You agree with my quadratic equation there? 16 minus 52. Everybody agree with that? So that's going to be equal to negative 4 plus or minus the square root of negative 36 all over 2, which is equal to negative 4 plus or minus j 36 all over 2. So by factoring out a j out of there, I'm just factoring out the square root of negative 1, which we know is equal to j. that is equal to negative 2 plus or minus the square root of 36 is divided by 2. So I have complex roots, which means my f of s equation is going to be equal to partial fraction expansion, a over s plus 2 plus b at an angle of theta over, now here's what's helpful. If you want to go ahead and write this coefficient very efficiently, this is a real part and this is the imaginary part. So this becomes s minus alpha quantity squared plus omega squared. Okay? So s minus alpha becomes s minus a minus 2, right? So that becomes s plus 2 quantity squared plus omega, which is in this case plus or minus 3, doesn't matter. So whenever you square it, you're going to end up with 3 squared. Everybody see how I did that one? Okay? It's easier and more efficient for you to write it as s plus 2 squared plus 3 squared because you know what the alpha term is and what the omega term is, because our cosines and sines always have omega terms in there and maybe real terms. So you need to separate those two to make it easier. So the first thing I'm going to do is solve for a. So remember, how do I solve for a? Can I do the efficient shortcut way, or do you want me to write it all out? Write it out? So a over s plus 2. Remember, I have to multiply both sides by whatever is under the a term. That's s plus 2. Plus b at an angle of theta over, and I'm just going to go ahead and write this out the whole way, and you'll see why it doesn't matter. S plus 2 equals 5 over s plus 2 times s squared plus 4s plus 13. Again, multiplying both sides by whatever under the a. And now I'm going to make sure I evaluate it at the root of that pole, or of that coefficient, minus 2. Everybody see that?
Is that where you have the under the 5 s plus 2, is that s squared plus 4s?
S squared plus 4s plus 13. It's this original part right here. So now I can cancel out terms. S squared goes away. Nothing to cancel out here, right? Even though you see this is s plus 2 right here, squared, I can't cancel one of those out because I'm adding a 3 to it, right? So you can only cancel out if it's multiplied. Since it's added, it doesn't go away. That cancels out, so I'm left with a plus b at an angle of theta over s squared plus 4s plus 13 times s plus 2 equals 5 over s squared plus 4s plus 13. And then I evaluate that at s equals minus 2. Right? Everything's been canceled out. So let me give me some more space here. So now I'm ready to go ahead and evaluate at minus 2. So a plus b at an angle of theta times s plus 2 when s equals minus 2. What does that equal? 0, right? This term is going to go to 0. So this is b at an angle of theta over s squared plus 4s plus 13 times 0. That's going to be equal to 5 over negative 2 squared plus 4 times negative 2 plus 13. So a is going to be equal to 5 over negative 2 squared is 4 minus 8 plus 13 is equal to 5/9. That's my value for A. Can we do B? Or do we need to pause for a moment? B? All right, so let's go for B. So I'll write it all out, LA over S plus 2. Now I'm going to multiply both sides by whatever is under the B term. Right? Just multiply both sides. And then I will evaluate at the positive omega term root. In this case, that's minus 2 plus 3j. So if I just plugged in omega in there, right, or j omega, I'm not going to get the right result, am I? Because it doesn't evaluate out to 0. So I have to include the real part, the minus 2 in there. Otherwise, it doesn't cancel out. So it always has to be the positive complex number in there to make that work. That's why it's negative 2 plus 3j. If I did the negative j, then I'd end up with the angle that's phase shifted essentially by 90 degrees. So let's multiply stuff out where I can. So this is a plus 2, s squared plus 4s plus 13, plus b at an angle of theta equals 5 over s plus 2, evaluated at negative 2 plus 3j. Right? What happens to this term right here when I evaluate it at negative 2 plus 3j? Anybody? Yeah, because this right here, that really is just this term right here, right? So it's s, whoops. It's s plus 2, quantity squared plus 3 squared. If I evaluate at s equals negative 2 plus 3j, what do you end up getting? You have s, which is negative 2 plus 3j plus 2 squared plus 3 squared. You can see the negative 2 and the positive 2 cancel. What does 3j squared equal to? 3 squared times j squared is negative 9 plus 9. What does that equal? 0. So again, that's why I needed that negative 2 to cancel out the positive 2 there. So this is going to multiply by 0. This doesn't go away. This becomes negative 2 plus 3j plus 2 equals 5 over 3j. So b at an angle of theta, I need a little help here, is 5 over 3j. What is the magnitude and the angle of that? I think I know what it is.
1.67
Very good. I think I was right. So 5/3 at an angle of minus 90. So my f of s, and I'm going to bring that here. My f of s is going to be equal to a over s plus 2, which was 9/5, right? Plus 5/3 at an angle of minus 90 times 1 over s plus 2 squared plus 3 squared. That's my f of s. It's almost perfect, right? I just need to have a 3 up here, right, to be omega squared over whatever that term is. So that means I need to divide by omega here, don't I? So my f of t is equal to 9/5 e to the minus 2t plus 5 over 9, right? Because 5/3 divided by 3 is 5/9. This is, whoops, forgot this one. E to the minus 2t sine of 3t minus 90 degrees. Pausing here because it's a little bit of an interesting, funky way to do it, but we're just plugging numbers in. Questions? Where are you stumped, if at all? Anywhere? Don't know where to go? Yes, sir.
Can you just explain how you're making the right half of that equation, like converting from 5/3 at an angle of -90 degree, and how you,
This one right here, how do I convert that?
yeah, how does that become what's right below it?
Sure, okay. So if I look at my table, in my table, there's an f of t and an f of s, right? So you just have to make the two look like each other, then you can go back and forth real easy. In the table, e to the minus alpha t sine of omega t looks like s plus alpha squared plus omega squared with omega, right? So when I look over here, right, I see that my s plus alpha squared is 2. Alpha is equal to 2. My omega squared is 3. I also need to have omega over here, right? I have 1. I need 3. So what I do is I just make this equal to, I have no idea why it does that. I have to contact the company because it just drops out all the time, and I'm not sure why. My omega has to be up there. So this number needs to be 3. So what I do is I always, when I go for my coefficients, I take the b at an angle of theta and I move it out front, and then what I'm left with is a 1 here. Then I just multiply that 1 by whatever I need up there. In this case, it happened to be 3. So I need 3 here, so I'm multiplying the numerator by 3, which means I have to multiply the denominator by that same value so that I'm only multiplying by 1, right? 3 over 3 is equal to 1. So I multiply the two together, and I've got a 3 here. So now I've got 5 over 3 at an angle of 90 divided by 3 out front. That's equal to 5 over 9 at an angle of minus 90. Okay? So if I want this to go into this form, let me move it up a little bit here. What I see is that it's all set up for me to look like this. This is just basically multiplying by a complex number, right? Do you remember in AC circuit analysis, how do you multiply complex numbers together? Multiply the magnitudes and add the angles. So what is the magnitude here? It's equal to 1, isn't it? So 5/9 times 1 is equal to 5/9. That's the magnitudes. The angles, right, have to be within the sine term. So that's e to the minus 2t. Inside here is 3t, because that's an angle, isn't it? Omega, which is in radians per second, times second is in radians, but that's an angle. Now, because I multiplied the number together, I add the phase shifts together, which means I add a negative 90 degrees. That's what I'm doing. Okay? Very important when you look at this problem. This is in radians, and this is in degrees. So if you're trying to evaluate those in your calculator to figure out what's going on, make sure you understand that one's in radians, one's in degrees, so they have to be converted to both radians or both degrees. and your calculator has to be in the right mode to be able to do this conversion correctly. Otherwise, you won't get there from here. Does that answer your question? It's all based on the tables. The tables reveal all. Just trying to make everything look like the table. And so multiplying by a constant is the same thing. We took advantage of that property. And guess what? 5/9 at an angle of -90, isn't that a constant? Does that change with respect to time? Just because it's complex, it doesn't mean it's not a constant. So that's why we can do that and it doesn't change any results. Questions? You want a homework problem to sort of reinforce? Okay. Let me, I'll pause the video and I'll pause the screen because I have to do this the old-fashioned way. So I'm pausing the video and I'll be right back. Okay, for homework, I would like you to find f of t for this f of s. So if you can't read it, let me write it a little more clearly. It's 12s over s squared plus 6s plus 5 times s squared plus 8s plus 41. That's the f of s. Doable? Tuesday? Let's see, that's November 3rd. Friday's the 1st, Saturday's the 2nd, 3rd, 4th, 5th. Okay? Any other questions on that one?
Do you have to leave it in that form, or can you factor? Actually, no, you shouldn't just leave it.
Okay, no question. Yeah, if you like to do a process, right, the way that you tackle any of these problems is find all roots, which essentially means quadratic equation, right? If you need to, you could do it 100 times or once or no times. But whatever you need to do, you need to find all the roots. Then you set it up in standard form. Right? Whatever standard form means to you, that basically means it's going to have it written out with its factored roots. And then 3, perform partial fraction expansion, right? So just basically set it up into the lowest order roots that you can based on the techniques that we've done. And then step 4, solve for your coefficients. Step 5, once you have all the coefficients, now make it look like the table. And then step 6, which is your last step, take to the time domain. And you got it. Okay? Questions? No questions? Fair enough. Okay, there we go. Last section is if you have repeating roots. So if I'm looking here, normally I would do f of s equals this way. When you do partial at fraction expansion, you have to start at the highest coefficient that you have, since it's an s cubed. Let me zoom in a little more. Since it's an x cubed, you're going to have your coefficient here, which is s cubed. Then you're going to go down to s squared and all the way to s to the 1 power, right? S to the 0 is 1, so you don't, or raising something to 0 is 1, so you have to worry about it. So this is how you would perform your partial fraction expansion for this one. So let's go ahead and solve for a. So I'm going to multiply both sides by whatever is under the a coefficient, right? In this case, it's s plus 2 cubed. Multiply both sides by s plus 2 cubed. Divide out my terms and evaluate at s equals minus 2, correct? Which is good because at s equals minus 2, this goes to 0, this goes to 0, and all I'm left with is a equal negative 1. So that's what we've been doing. Let's go ahead and do that now for b. So we're going to multiply both sides by whatever is under the b term, in this case s plus 2 squared, and cancel out my terms. What I'm left with is 2s plus 3 over s plus 2 equals a over s plus 2 plus b plus c times s plus 2. Now I would normally evaluate at s equals minus 2, right? That's our approach. Except what happens if I put minus 2 in here? That goes to infinity. That goes to infinity, doesn't it? So this is not going to work. I can't go and actually multiply by whatever the b term is and evaluate there. It's going to not work for me. So let's go back to what we did for a. So we're going to go back here, and we're ending up at this location, right? This is how we solve for the a term. But instead of actually solving for a at this point, or you could, right, if this is your first term, I'd like to get rid of the a term. Is there a mathematical property that gets rid of a and only a? Remember I said we're going to be able to get rid of most of calculus, but not all? What calculus function would you do to this equation? Yeah, if I take the derivative of this entire thing, what happens to the derivative of a constant? Goes to 0, right? So if I take the derivative of that expression, the derivative of 2s plus 3 with respect to s is just 2, right? It's just 2 plus 0, so this goes away. What's the derivative of a now with respect to s? 0. Goodbye to my a term, which is what I wanted. For my b term, now I take the derivative, the first derivative of bs plus 2 with respect to s. It's just going to be b times 1. What do you know? I'm left with b. My a is gone, right? A is no longer there. It's gone. And the other nice thing about taking the derivative is look what happens here. I've got 2 times c times s plus 2. So remember when I have a higher order power, I only want to solve for b, not c. So if I still evaluate at that root, right, which is negative 2, doesn't the c term go to 0? So if I evaluate at negative b, I'm only left, or negative 2, the only term I'm left with is b. And so b equals 2. Okay? So if you have repeating roots at the same exact location, meaning you have something that has s plus some alpha to a number greater than 1, so we'll call it n, you just go ahead and do partial fraction expansion like you normally would, write it all out the coefficients, and then just take the derivative, multiply both sides by whatever is under that, whatever the maximum is, and then just take the derivatives down that are necessary to do that. Okay? So to get c, right, we just take another derivative of the equation. So you'll notice I multiplied both sides again by s plus 2 cubed, and I'm left with this expression right here, right? I take the first derivative of it, and here's what I get, which is great, but I want to get rid of the b term. So if I take the second derivative of this, Now all I'm left with is this. So 2 times c equals 0, so c is equal to 0. So my partial fraction expansion for this problem, which is 2s plus 3, s plus 2, oops, all over s plus 2, oops, that's not right, that can't be right. Just 2s plus 3, I think. Yeah, 2s plus 3 over s plus 2 cubed. So let me get rid of this one, because that's not correct. So that is going to be equal to, it's going to be equal to a over s plus 2 cubed plus b over s plus 2 squared plus c over s plus 2. I solve for a. A is equal to, where are you, A? A is equal to minus 1. So that's going to be equal to minus 1 over s plus 2 quantity squared plus 2 over s plus 2, that quantity squared, plus 0 over s plus 1. This essentially looks like the table, but if you look at your table, you have s plus alpha to the n is going to be, so 1 over s plus alpha to the n is equal to, let's see, is it t to the n minus 1, e to the minus alpha t, I believe. You can take a look. So if it's multiple roots. So my f of t here is equal to, so you notice this is 3 over here. So I have a 3, so I need to go negative 2 t squared e to the minus 2t plus 2 t e to the minus 2t plus 0. Let me write that out a little bit neater. Sorry about that. F of t equals negative t squared e to the minus 2t plus 2t e to the minus 2t plus 0. So anytime you have a squared higher order term, you manifest that with a t term up there. Okay? So that's really how you deal with multiple roots. Multiple roots you don't often have to deal with because most real-world systems, you just would not have the same pole in the same location. That's pretty atypical, but you do it for completeness. But doing the approach where you had b at an angle of theta, many systems have a response where it has an oscillatory response. That's called an underdamped response. You're going to see that that happens a fair amount. So being able to do that one is especially critical, especially when you go on a 325. 324, we just make sure that we're complete, but that's the idea. So I think that that is it for Chapter 5. Questions? All right, so on Monday we are going to have lab, but it's going to be exam review. So here's the question. Do you want an exam on Tuesday, Thursday, or the following Monday during lab? Who votes for Monday? Okay, so we'll have exam 2 that following Monday. So what did we say? That's November 11, I believe, during lab. It's going to cover chapters.
There's no class that day. That's Veterans Day, yeah.
Oh, okay. So then it either has to be the Thursday before or the Tuesday after Veterans Day. Tuesday? So that's going to be November 12. Sorry about that. I'm not putting down the veterans, so we shouldn't make up any jokes about that. So we'll do the exam. It's going to cover chapters 4 and 5. You can bring your FE review manual. Okay? How's that work? So Monday, come to class with any questions. We can go through Laplace. We can do hundreds of examples, which is what I would do. You'll notice here, there's a lot of homework. That says 1 through 21. So that's 22 homework problems just for there, plus these other ones. There's about 35 problems to do. So if you haven't been tackling them, I would encourage you to do them because you get a lot of good practice. Okay?
How rigorous are those homework questions? Like, are they
Not too bad.
not too bad?
No. There's a couple of derivations. These first ones, I think, are basically make it look like the table and use that. The other one, there's 1 or 2 derivations where you do the sine or the cosine. You can do the approach that they recommend, or you can use the Euler's identity approach that I presented. Either one works. So it's up to you. But doing the homework will prepare you best for the test, in my opinion. But this other practice problem that we have, which is, where are you? Right here? Nope, not that one. Someplace over here. There we go. No. Doing this one will be a good example, but we can do many of these practice problems on Monday to help you with that. So we got a few more minutes of class. Anything you want to talk about, or would you like to start your weekend early? Who votes for weekend early? Who votes for more practice and more work? Nobody? All right. Have a great weekend.